So let us start today's session. Hello everyone, I am Tanuka from ISC. So welcome to the fourth week of deep learning problem solving sessions. So in today's class we will be mainly talking about problems on optimization and some basic neural network concepts. So let's get started. So the first problem that we have for today is on optimization perspective. So the question is, you have been given this cost function, this is your cost function. So theta is your parameter and the cost function is theta square minus theta plus 2. So given this cost function, what is the weight update rule for gradient descent optimization at step t plus 1, and we have to consider alpha equal to 0.01 to be the learning rate. So as we know, in gradient descent optimization, what is the idea? The idea is you have a cost function, you proceed towards the negative of the gradient, because let us say you are in this is some loss function profile and you are at some point, you want to go to the minima, you should proceed in this direction, that is the idea. So we take the derivative at this point, which will give us this direction, and we take the opposite to have the have our movement towards the minima of the function. So we descend towards the minima and we use the gradient direction for this. That is why this is the gradient descent optimization. So if j theta is your cost function, then first thing is you have to compute the gradient, that is del j del theta, and once you have that, your weight update or parameter update rule will be something like theta plus 1 will be theta t plus 1, which is the estimate at the step t plus 1, that will be theta t minus eta times or alpha, sorry, here this is alpha they have mentioned for the learning rate, alpha times del j del theta, right. So here your j of theta is theta square minus theta plus 2. So your del j del theta is supposed to be 2 theta minus 1. So your weight updation rule at the step t plus 1 will be theta t plus 1 equals to theta t minus alpha, which is here given as 0.01. So 0.01 times del j del theta, what is that is 2 theta minus 1, 2 theta minus 1, which is the option A in this particular question. Theta t plus 1 equal to theta t minus 0.01 into 2 theta minus 1. I hope the idea of gradient descent optimization is clear to everyone. So you have a cost function given, you need to compute the gradient of that cost function, that is the direction of maximum change, and you move towards the opposite of that. So whatever was your estimate at some tth step theta t, you subtract del j del theta times the learning rate to obtain the next estimate. So this becomes your formula for the gradient descent, and for this question it reduces to this thing. Now given that, the next problem says, can you identify in which of the following graphs gradient descent will not work correctly? So can anyone answer this question? Which one do you think is the case where gradient descent will not work correctly? Any guesses, guys? You can just write the answer in the chat, or you can also unmute and speak up. So these two graphs that are given, these are basically the loss landscapes are given. So these are some 3D plots which shows the loss surface, how it looks like. So you have to achieve the minima on this surface, whatever is that loss surface, you have to go to the minima of that, and you are supposed to use gradient descent. Now, so what you do in gradient descent, you always go compute the direction of the gradient and you go opposite to that. Now, in which of these two loss landscapes do you think gradient descent will not work? Okay, so I do not see any answer from anyone. Okay, so in the first graph, if you consider this one, this has a well defined minima which will be somewhere over here. So any point you start, you can go towards the opposite of the gradient and you can reach to that minima. But in this particular case, the second one, once let us say you start from somewhere here, anywhere, but once you reach this region of the graph, here it's, if you see, it's kind of horizontal with the xy plane. So here once you reach here, your update with the gradient will be very less. So you will not be able to move out of this region, you will just be stuck at this region and will not be able to go to the further minima points. This is basically the saddle point case, which is a classic case for gradient descent. So if this is the loss landscape, it will not gradient descent will not work here, it will get stuck once it reaches this region, because the gradient will be really small and it will not be able to go out of this portion of the graph, and it will not be able to go to the actual minima. Okay. So for the first graph it will definitely work, but for the second one it will not. So let us move on to the next one. Now, so you have studied about the batch gradient descent and stochastic gradient descent. So in batch gradient descent, you take all the training samples together, compute the update based on all the training samples and update the weight based on that. But in stochastic gradient descent, you take one sample at a time, you update the weight values just based on that sample. So for each sample, you compute the loss, the derivative of it, and you update the weight vector based on that. But in case of batch, you have all the cost combined from all of the samples and you update on top of that. So here these two graphs show the loss function of the cost function value with the iteration, how it is minimizing. In one of them is using the batch gradient descent and another of them is using the stochastic gradient descent. Now can you say which of the following two figures is for batch gradient descent and which one is stochastic gradient descent? Can any one of you answer for this? Money is saying graph A stochastic. Okay, anyone else? So does everyone agree with the Money that graph A is stochastic gradient descent? Okay. So, Mani, your answer is not correct. Graph A is basically the batch gradient descent. This is batch and this is stochastic. So, the thing is, when you have just one sample, when you just have you are updating just with one sample, your loss varies a lot. The jitteriness that you are seeing in the curve, this jittery thing comes because you are updating just with one sample. So, let us say you are at some iteration, let us say you are somewhere here, this is your loss. Now, you are just taking one of the training samples and you are updating the weight vector just based on that sample's cost. Now, what it can result in is this sample is now, let us say earlier it was getting misclassified, now it is getting correctly classified, but some 2-3 other samples might get misclassified because of this thing, because here you are considering just one sample for updating your cost function or your weight vectors. So, you are not at all considering what will happen because of this to the others. So, you keep on doing this thing for all of this, finally you will reach to the minima, but at each point you are just checking one of them and you are updating. So, it is kind of fluctuates a bit. So, you are making one sample correct, another 2 is going wrong, again you are making another sample correct, some random other sample is going wrong. So, it is kind of jittery throughout, but when you are doing as a batch, so you have the estimate of the loss function for all the samples. So, it is kind of averaged out over the entire set and you are updating using the information for all. So, the curve that you get is kind of smooth, that random fluctuations just because one has gone wrong, one has gone correct, those things does not come up, that those effects are averaged out. So, you get a smooth curve, whereas when you are doing stochastic, on updation it becomes smooth with more, okay, let us see, on updation it becomes smooth with more training vectors, therefore first one is, first one is batch, correct. When you have more training vectors, you are taking all of them into account for updating the vector, then this random effects of each one of them gets balanced out and you get a smooth sample, smooth curve of the cost function. But stochastic is just one, so you get this jitteriness. If you are using a mini batch gradient descent, that will be some way between these two. It will not be that much jittery as the stochastic one, but it will also not be as smooth as the batch one, because there also you are not considering all the samples, you are just considering a mini portion of this. So, once you have very less number of samples, it becomes jittery. Okay, I hope this is clear to all of you. If you have any doubts, you can just stop me at that point itself. Now, let us move on to this one. So, here again we have given you the cost function, which is 0.25 theta square, and that cost function has been plotted with theta. So, in this graph, this y axis is j theta, x axis is theta. Now, 3 points are shown on the graph, point 1, 2 and 3. So, in which point do you feel the magnitude of weight update will be more? So, what do you think, at which point 1, 2 or 3, where the weight update magnitude will be the highest? You are again you are using the gradient descent algorithm only. So, your loss function, cost function is j theta, and your update, as I wrote last time, is theta t minus alpha times del j del theta. So, if you just want the magnitude of weight update, so the magnitude of change in each step, then that magnitude is basically alpha times del j del theta. So, this is the change you are making to the weight at each step. So, at which point do you think this quantity will be the highest? So, can anyone tell me what will be the value of del j del theta? Okay, Neelam is saying 0.1. Yeah, Neelam, you are correct, absolutely. So, here your j theta is 0.25 theta square. So, your del j del theta will be basically 0.5 theta. So, this gradient is directly proportional to theta. So, if you see this quantity, which is the change in your weight or magnitude of your weight update, this thing is basically the magnitude of this del j del theta. You can just ignore the alpha because that is a kind of constant quantity. So, this is basically, this is proportional to, if I say, magnitude of this thing. So, this is basically, it is linearly proportional to theta. So, where the theta value is maximum, there you will get the maximum change in del j del theta. So, among these 3 points, 0.3 to 1, if you see, here the theta has the highest value, which is 6 in this case. So, here you will have the maximum value of del j del theta. Yeah, Mani, you are correct, the magnitude will be 3. Because at this point theta is 6, so del j del theta will be 3 of course, and for the other two also you can compute, and you can see that maximum value of del j del theta will come at this 0.1. So, when you are at this point you will have the maximum update in the weight. So, you can see here when you are at this point you have maximum update, and once you are coming closer to your solution is here, this is your minima. Once you are coming closer to your solution, your weight update will keep on reducing. So, it is like as you are reaching your destination, your speed is gradually reducing. So, once you are much away, you are going very fast. So, your weight updation are much larger, and once you are almost there, you are taking small steps to reach at precisely at the final point. So, that was about optimization part. Now, we will move on to the neural network concept. So, first let us see this problem. Let x and y be two features to discriminate between two classes, class 1 and 2. The values and class labels of the features are given here under. What is the minimum number of neuron layers required to design the neural network classifier? So, at least how many number of neuron layers you should have to perfectly do this classification? Can anyone guess what should be the approach to address this problem? Like how should we proceed to go about this? You can just unmute yourself instead of writing that much. So, 6 neurons, okay, 6 neurons, that is fine, but how many layers do you need? Is it a single layer network you need or a double layer network you need? You need 3 layers. Why do you think so? Money, right? So, you are saying you need 3 layers, is it? So it is not 3 layers. So let us see this. So if in order to decide the minimum number, first what we should check is whether we can do it with one layer or not. So if this is a linearly separable problem, then you can simply do it with one layer neural network. You don't need a non-linearity component in this. You just have a single one layer network. You can do a linear classification with that. So for that we need to first check whether this is a linearly separable problem. So for that, let's plot our data. This is x, this is y, let's say. So the first point is at 0, 2, and this is from class 2. Let's say I mark class 2 by dots. Next one is at 1, 2, that is from class 1. Next one is at 2, 2, that is also from class 1. Next one is at 1, 3, okay, that is also from class 1. Another one is at 1, minus 3, that is from class 2. Okay, the drawing is not that great, but anyway. So these are the 5 points that you have. These 2 points 0, 2, 0, 2 here and 1, minus 3 here. These 2 belong to one class, and 1, 2, 1, 3 and 2, 2. These 2 belongs to one other class. So you can easily see that you can draw a straight line in between them and they are linearly separable. So if they are linearly separable, you can easily have a single layer neural network to classify these. So for this particular training data, only a single neuron layer is required to design the neural network classifier. So that is the correct answer. This is linearly separable. So one neuron layer needed. Okay. Mani, I hope this is clear to you.
Yes, ma'am.
Yeah. Okay. Now the next one. So here you are asked the number of weights including biases to be learned by a neural network having 3 inputs and 2 classes and a hidden layer with 5 neurons. What is that number? So basically you have 3 inputs. Let's say these are the 3 inputs. This is the input layer. Then you have a hidden layer with 5 neurons. This is your hidden layer, and last you have sorry guys, and the output you have 2 classes. So let's say we have 2 neurons at the output. So in this first layer, so this each input will go to each of the hidden neurons, right? So what does each hidden neuron do? It simply does a weighted sum along with a non-linearity, right? It does WIXI. f of that over all I. So, if you consider first this neuron, it will do linear combination of all these 3 inputs and it will do a non-linearity. So, if it needs to combine 3 of these inputs, so it will have 3 weight values, right, for one corresponding to this, one corresponding to this, one corresponding to this. And finally, actually here we generally have a bias term as well, plus bias. So, for each neuron you have one bias term also. So, 3 plus 1 for this neuron. Similarly, you have 5 neurons. So, from the first layer you have 5 neurons, each with 3 plus 1 parameters. So, total you have 20 parameters from the first layer. Now, from the next layer, if we say that the output has 2 neurons, then each of these neurons are again combined to all 5 of these outputs. So, each will have 5 weights along with 1 bias. So, in this layer you have 2 neurons, each with 5 weights and 1 bias. So, total 12 number of weights in and biases, total 12 number of parameters. So, combining these two you have 32. But you can think of actually this question was supposed to be framed slightly differently. The question should not have been 2 classes, there are 2 neurons in the output layer, because if you have 2 classes you can also have a single neuron at threshold that output to get 2 class labels. So, in that case you will just have 1 neuron at the output and that will have just 6 values. It will just combine the 5 outputs of the hidden layer and 1 bias term. So, total number of weight parameters from the second layer will just be 6. So, combining first and second layer it will be 26, but in this case this question asks for 2 neurons at the output. You can so if you have a 2 class problem you can have 2 neurons also, you can have 1 neuron also. If you have 2 neurons your output will be either 0 1 or 1 0 like that, but if you have a single neuron you can just threshold on that value as a sigmoid or something and you can from there also get the class level. So, I had a question here, madam, why do we add bias term? So, basically the weight vector that you are giving that I would what how should I say this? So, when you do linear combinations, for example, straight line, if you have, the most general way is y equal to mx plus c. So, you do not always expect the line to go through the origin, right. So, here also you do not always expect that the combination of these so, basically this bias term gives you that shift in the separating plane. So, you are modeling a linear function. If you just ignore this f thing, you are just modeling a linear function with each of the neurons. So, unless you add a bias term, it is just a line passing through the origin, but it may not always be that case. There might be some shift in the line. It might be it is like this and light is placed here, then you will not be able to model that that type of combination through this if you just do not use the bias term. So, to have that also we use this bias term here. So, it is basically just to have a shifted output for this.
Madam, this bias term will go on adding to all the neurons which is there, hidden to output.
So, for each neuron you will have a different bias term, because they each of them are modeling a different feature. So, each will have a separate bias term. So, you can think it this way also. So, if you let us say you want to do a classification and you want to use a linear combination of your features as your linear combination of your inputs to obtain the estimate based on which you will do your classification. So, your input you have three values, you just try to do a linear combination of this to get to one value, and you just classify based on that value if you want to do that. Then when you are doing this WIXI, you get some range of values. Now, let us say for one class this combination goes here, another class this combination goes here. So, you can just put a threshold over here somewhere, and you can do the classification. So, if this thing is below a threshold, you classify it to one class. Now,
Madam, hello madam.
yeah.
If I don't add this bias term, will the network will have problem in classification?
Your network, there might be cases where adding the bias term can better model the things. For example, this only that I am giving the example now. So, if you just you are combining, let us say you have just a single neuron, just one neuron, you have 3 inputs, let us say x1, x2, x3, and you are doing the classification using a threshold kind of non-linearity. So, below some threshold tau, you put it to one class, after that you put it to another class. Now, if you do this W1, W2, W3 are the 3 weights. So, you do this linear combination, this will be done in this neuron, and you are basically doing a thresholding on top of that to get the output. Now, if you want to have a like let us say standard non-linear function. So, let us say this you will do as a threshold function that we define, that after 0 will give it to one class, below 0 will give it to another class. If you want to have that kind of standard thing, you can simply write it like this. So, this term, that the threshold that you needed, that you take to the left hand side, that is basically your bias term coming in. So, once you have that bias term in this part, now you can threshold at 0. So, this is also another intuition of having the bias term. You are combining it to a single value. Now, you need to threshold on top of that. Instead of thresholding at some random level, which will vary from case to case, from data to data, you want to threshold it always at 0. So, you add a bias term in the left hand side itself. So, adjust it so that you can threshold it at 0. This is the kind of, this is another intuition behind this. Does that make sense to you? Money, right? Money, does that give you some intuition about the bias term? Okay, fine, great. So, if that part is clear with us, we can easily solve this problem now. This is similar to the concept that I was telling you right now. So, here we are given a single neuron and that has x1, x2, x3, 3 inputs and 3 weights are there, and your y is some phi function which is a nonlinear function on top of this weighted combination v. So, here your phi function is given like this. So, your v is, when it is greater than equal to 0, you have your phi value as 1, otherwise it is 0. So, let us go through the problem once. Consider the unit shown in figure 1. Suppose that the weights corresponding to the 3 inputs have the following values. The weight values have been already given, and the activation of the unit is given by the step function. So, if it is greater than 0, you put it 1, otherwise 0. Calculate what will be the output value y of the unit for each of the following input patterns. So, what will be the output value for x1? Can someone compute for me? So, the formula what we use, what we know, basically this neuron will do summation of wi xi plus the, here we do not have any bias term. So, Mani, for your example here in this case they are not using any bias term for this network. So, we do not always use the bias term, but sometimes when we use the bias, for some cases where you have to adjust your threshold accordingly or adjust the position of your planes accordingly, there you need to introduce the bias. That can give your model better capacity to learn the scenario. So, here simply we have wi xi which is v and I is here 1, 2, 3 and our output is phi of this v, right. So, if we consider the first example, point 1 which is 1, 0, 0, in that case your v will be just so it will be w1 x1 plus w2 x2 plus w3 x3. So, x1 x2 x2 x3 are 0. So, it just becomes w1 which is 2. In that case the output for this becomes, this is greater than 0. So, the output becomes 1. This is for P1. Similarly, if you do P2, then your V will be x1 is 0. So, no contribution from w1, x2 x3. So, it will basically be x2 x3 are 1. So, w2 plus w3, that is minus 3. So, your y will be 0 because it is less than 0. 1 0 1 0 answer. Okay, let me check for P3 and P4 quickly. 3, so y will be 1, and P4 this is minus 1, so y will be 0. 1 0 1 0, yes, 0 1 0, yeah, both of you are correct, absolutely. So, these are the outputs. So, this is basically the smallest element of a neural network, the one single neuron. Now, in the next problem, that is also a similar one, just the functioning of the neuron is slightly different in this case. So, here we are assuming a single neuron with 3 inputs and a single output, and the weight of the neurons are 4, 5, 6 respectively, and we assume the activation function is linear with a slope of 4. In this case, what will be the output of the input pattern? Can some of you compute this? These are your weights 4, 5, 6, and your input pattern is 4, 2, 3. This here you get V, and what is your y? Y is basically a linear, activation function is linear with slope of 4. So, it will be 4 times V. So basically if you compute V here, that is 16 plus 10 plus 18, $44 and your Y will be 4 times 44 176, correct. So these are very simple stuff. Now let us move on to a slightly different one. So here we have a feed forward neural network with one hidden layer. So this this layer is your input layer, this layer is your hidden layer, and this layer is your output layer. Neelam, you have any doubts? Otherwise you can keep yourself on mute. Now here what is the problem? The weight on connection between nodes I and j is denoted by wij, such as W13 is the weight on the connection between nodes 1 and 3. Then all the weights are given in this chart, 1, 3, 2, 3, all of them are given. Now each of the nodes 3, 4, 5, 6, this uses the same thresholding function as the activation function, where V is the weighted sum of a node. So if your weighted sum of the node is greater than 0, your output is 1, greater than equal to 0. Each of the input nodes 1 and 2 can only receive binary values, either 0 or 1. Then you have to calculate the output of the network for each of these 4 input patterns. So let us try to do that. So this is basically your network, right? So you have 1, 2 here, then you have 3, 4, 5, 6, and all of these are connected. Now the weight joining ij is given for all of this. So the weight joining 1, 3 is minus 2, 2, 3 is 3. So weight joining 1, 3, that is this weight joining node 1 to node 3, that weight is minus 2, and node 2 to node 3, that is this one, is 3. Now 1, 4 is 4, 2, 4 is minus 1, 1, 4 is 4, 4, 2, 4 is minus 1. 2, 4 is the weight joining node 2 to node 4. Now that was for the first layer. Now for the next layer, 3, 5 and 4, 5 are 1 and minus 1. 3, 5 is this one, 1, and 4, 5 is this one, minus 1. 3, 6 minus 1, 4, 6, 1. 3, 6 minus 1, 4, 6, 1. And these are your final outputs, y5, y6. This is y3, y4. Now you have to compute. So here what you can see initially, let's say, is there any name? Okay. Let's say these are your inputs x1, x2. So your y3 is basically minus 2x1 plus 4x2, and on top of that you have the non-linearity activation function phi, right. This is your y3 minus 2x1 plus, I am sorry, that is not 4, I confused the numberings that I did. This should be 3, I guess. The weights that should be there, since we are connecting the output of the node 3. So, we will consider basically, let me write it down once. We will basically consider W13x1 plus W23x2, right. Now, 1 3 is minus 2, 2 3 is 3, right. So, this is basically minus 2x1 plus 3x2, that is the output y3. Similarly, you can have y4. y4 is basically, so x1 is connected through the weight 4. So, 4x1 plus x2 is connected through the weight minus 1. So, minus x2, that is your output y4. Now, when you go for y5, y5 is basically connected to y3 and y4. These two are coming as input to y5. So, y5 is basically phi of y3 minus y4. And similarly, once y6 is phi of y4 minus y3. So, these are the different formula. These y5 and y6 are your final output. Now, let us take the first case. Let us say point P1 is your 0 0 point. So, when you have this 0 0 point, your y3 will basically be phi of 0, and the function that we have defined, that phi function, this is 1 if your v is greater than equal to 0. So, here your this will be phi of 0, which is 1, right. 1. Similarly, y4 is also 1 because these two are again 0. Now, both of them are 1. So, y5 is basically phi of 0, again 1, y6 is also 1. So, your output is 1 1 for the first point 0 0. Now, if we take the second point 0 1, then what will be the case? Now, your y3 will become phi of 3, right. This is 1, and y4 is phi of minus 3. So, this is 0 because phi is 1 only if, oh sorry, y4 will be, use this formula. So, x1 is 0, this is minus 1. So, it will be 0 because phi is 1 only if the input is greater than equal to 0. Now, if we compute y5, it will be phi of 1 minus 0. So, phi of 1, that will be 1, and y6 will be phi of 0 minus 1, which is minus 1. So, 0. So, the output will be 1 0, y5, y6, 1 and 0. I will compute one more maybe. So, if we consider the point, let us say 1 1, then your y3 will be if x1 x2 are 1 1, so this is phi of 1 which is 1, so your y3 will be 1. And your y4 again this is 1 1, so phi of 3, so y4 is also 1, y5 y6 both will be 1 because y3 y4 are equal, so both of these goes to 0 and phi of 0 is 1, so your output will be 1 1. Similarly, you can compute for 1 0 also. So, this is how you compute the output when you have a multi-layer neural network. This is the way you do it. Now, let us take a similar case here, but here we have introduced the bias term. So, these and these corresponds to the basically the bias term. This is the not input, simply you are giving +1 and you are combining with some weight. So, basically it leads to the bias term. So, in this problem, this is an implementation of the XNOR function. These will be the weights if you try to do a XNOR function you on x1 and x2 using a neural network. Now, the activation function for each node is same, that thresholding function. Now, you have to consider x1 is 1 and x2 is 0. What will be the output for the above network? So, your x1 is 1, your x2 is 0. So, what will be the output of your network? So, if we see this, first let us say we compute A1. So, A1 is connected to x1 through -1 and x2 also through -1 and the bias term is 0.5. So, now x2 is 0. So, we have minus 0.5 because actually what we have is -1 into 1 plus -1 into 0 plus 0.5. So, -1 plus 0.5, you have -0.5 here. Now, on top of that you will have this activation function. So, since this is negative, so the activation function will lead to 0. I should actually write f of this. So, that is 0. A1 is 0. Similarly, you can compute A2, which will be f of the bias term is -1.5 here and both the weights are 1. So, you will just have 1. So, this is again f of -0.5. So, this is 0. Both A1, A2 are 0. Now, if you compute A3, you can see both A1, A2 are 0. So, no contribution for this, only the bias term comes up, which is -0.5, f of that is equal to 0. So, this also confirms the XNOR function is actually happening 0 1 or is the XNOR function output should also be 0, and this is how you compute when you have the bias term along with the weights. Okay. Now, this one. Consider the following neural network shown in the figure with inputs x1, x2 and output y. The inputs can take the values 0 and 1. Then you have to tell which logical operation this network is actually performing. Can someone give me the answer for this?
OR function.
Sorry?
OR function. X1 plus x2 equal to 0.5.
OR function. Okay. Okay. Let's see. Let's have a let's compute the answer for this. So, what is your y here? we will define the same f of v is 1 if you have v greater than equal to 0 and it is 0 else. Let us say we define the same non-linear function. Anyway, so your operation will be minus 2x1 minus 2x2 plus 1. This is the output function for this case. So, if you just take the chart, so your, let us say first your both x1 x2 are 0. So, y is basically f of 1 which is 1, is it? This should be something like this, right?
So it is NOR function.
Yeah. So, this is NOR operation is being performed. So, I hope that is clear to everyone. I had one answer that it is OR function. So, that is not the case. If you can simply write down the equation of your output and compute the output. So, it is the NOR function. Yeah. Now, let us move on to the last problem for today. So, let us say x equal to minus 1035 be the input of ith layer of a neural network. On this we want to apply softmax function, then what will be the output of it. So, softmax function, if Si is the output, the ith value of the softmax output, then how is it computed? It is computed as exponential of xi by summation over all I exponential of xi. This is basically kind of mapping your xi values to a probability distribution by doing this kind of normalization. So, this is basically the equation e to the power xi divided by summation of overall I e to the power xi. If you compute that, you will get the softmax output for each value. So, what will be the answer for this?
2.
Yeah, 2 is the correct answer for this. I am not computing it. You can just compute and cross verify. 2 will be the softmax output for this function.
If we add, it should come to 1, right? It should come to 1 as well as think, right? We have the numbers increasing, so it is also increasing. For 3 it is the more, and 5 it's more.
3 and 5, yeah, right, absolutely. For 5 you should have the highest value, which
And also,
is, yeah, except for option 3, that is the case for all the options.
correct.
And also this is, you are mapping to a probability distribution, so it should add up to 1, all of this. Yeah, absolutely. Okay, that was the problems planned for today's session. So if you have any doubts, you can ask at this point. So as you know, like the drill for every day, I'll keep this session open for some more time, but I'll not be solving any more problem. If you have any doubts, I'll try to answer that.
Ma'am, could you please suggest one best book on DL?
Best book, if you say so, I'll tell
Because
you.
it's difficult to refer too many books, and in internet also a lot of
Yeah,
material is available.
yeah,
So
right.
based on your knowledge and experience, I request for one book from your side so that we can have our own house book purchased.
So there is one book. I'm just not being able to remember the name. I'll just search and tell you. Just a moment.
G.
That Goodfellow book is there for deep learning. That is also available. The PDF is available online. But the thing is, that book is slightly difficult to read. But that's the gold standard book for deep learning. But yeah, it's slightly difficult to read. If you, I also don't know about a very like easy to read. It is easy to understand book of deep learning. But that's the standard one, and some of the concepts will also be there in some pattern recognition books, I guess. But if you want a complete deep learning book, Goodfellow book is the like gold standard, you can say.
So in that, any latest edition is there, because there could be too many variants and editions too. So, or
That
latest one.
that I'm not sure which one is the latest edition.
G. Okay, I'll check. I'll check. Thank you.
Any other question from anyone?
Ma'am, earlier 3 assignments I could not submit because I was busy in my official activities of R&D in defense.
Okay.
So, is it possible to get fresh assignments so that I can submit, if at all allowed?
I don't think so, but I am also not the correct person to say that. I guess you
Ji.
can once mail to them, NPTEL team, if they can allow that. I don't know about that administrative part.
Okay, okay. I thought as a special genuine case, if there is some provision, then I can take
Maybe there can be.
advantage of that.
Huh, huh.
Otherwise, okay, no problem. Okay, thank you.
So for those who are joining, okay, for those who are joining now, so we started the session at 4 as scheduled. So I have already solved the problems that were planned for today's session. If you have any doubt from your side, you can ask that. So today we were talking about optimization and neural networks. Any doubts in any of the concepts covered so far, you can ask that. Otherwise, if you want to go through the problems that I was solving, you can refer to the recorded video of this session. week 5 problem solving session will be. So week 5 problem solving session will be in the next week. So next Saturday I'll be taking the problem solving session, and the other 2 TAs will take on next to next Tuesday. So just after we have our sessions, we upload the links in the sheet that is shared in your course web page. That you have to talk to NPTEL people. So they asked us to start on February 4th, I guess, February 3rd or 4th. That was supposed to be the first week, so we are counting from that point. So currently we are at week 4. Next week will be at week 5. Yeah, I know it was that way for previous semester. I also did T-ship in some other course. We used to have the problem solving session before the assignment deadline. Yeah, I remember that. But for this time, this was the date scheduled for us to start. So that's why we are going week by week. Oh, nice to know that. Yeah, the session is not over. If you have any doubts, you can ask those. But the problem solving part from my side I have done. So any doubts if you have, you can post that. We can discuss about that. And if you want to look into the problems that I solved, you will get it in the recorded sessions. Okay, so I'll close the session for today. Thank you guys for joining. We'll meet again in the next Saturday for the next session. Thank you.
Thank you, ma'am.